So live lecture will start after a short time. Hello friends, welcome back to the online classroom. Today discuss the concept of oscillators. So the what exactly oscillators are. So you all know when you studied physics, you already know about oscillations. So these oscillators work on the principles of oscillation. So oscillation may be termed as a sustained oscillations, which will give a periodic waveforms, or you can say a periodic repetition in periodic manner. So these are the oscillations. So you have already know certain experiments for different types of oscillations. So now we'll move on to the what exactly oscillators are. So to understand for these oscillations or oscillators, so you all know while doing practicals, you also remember that you are using function generator to give input signal for your different amplifiers or several other practical applications. So from function generator, you're actually getting a input signal. So So to that function generator, so it is a generator means what? It is generating a electrical signal. Either it is a sine wave, or it may be a triangular wave, rectangular wave, or any pulse. So that function generator generates a signal, maybe periodic or non-periodic, sine wave or non-sinusoidal waves. So now in this chapter we'll see how to generate a sinusoidal or non-sinusoidal signal. So earlier we have seen the amplifiers. So amplifiers, what is the function of amplifier? It increases the strength or power of the signal. So in many electronic devices, it is required a source of energy. As we are going giving a DC source to different amplifiers, but other than DC, when we require a AC source, in case when you are just doing a practical, performing a practicals of amplifier, you will need a AC source or AC signal for the amplification. So from where this AC signal you get, either you get it from your electrical supply, your main supply in your home, but it has a fixed frequency. So for electronic needs or devices, you will need or you require a sinusoidal or periodic signals of different frequencies. So for that, you have to create a certain device so that it generates a different signals of different frequencies. So it is done by using oscillators. So many frequency signals, so it may range from few hertz to megahertz. You will require these frequency signals. So these frequencies or signals can be achieved by an electronic circuit known as oscillator. The oscillators have variety of applications in telecommunications as well as electronics. For example, you know that we can use the sine wave as a carrier signal. So you may have studied it in your communication subject, that to use the sine wave as a carrier signal for modulation and demodulation. So while studying, have you ever wondered from where we are getting this carrier signal? So to get that carrier signal, we have to build a certain electronic circuit which will create or generate that signal of that frequency. So in very much of these electronic devices, you will require a signals of different frequencies. For that you are going to use oscillators. So in radar applications, there also we use oscillators. In computers and other electronic devices, there are also oscillators are used. So we have already seen the positive and negative feedback. So difference between positive and negative feedback we have already seen. So amplifier with positive feedback having a closed loop gain. So this closed loop gain AB dash greater than open loop gain. So you know that closed loop gain is gain with feedback and open loop gain is gain without feedback. So this AB dash greater than AB results in instability and it operates as an oscillatory circuit. So how this instability is causing the circuit to oscillate and it is generating a frequency, we'll see in our subsequent points. Also, an oscillatory circuit provides a constantly varying amplified output signal of any desired frequency. So you may require different sort of frequencies. Okay, at first time you may require 1 megahertz frequency. After a while you may want 10 megahertz of frequency. So for that you may also need a varying amplified output of a signal. So for that we need a oscillator. So first we'll see comparison between amplifier and oscillator. So here the first diagram you can see the amplifier and in the second diagram you can see the oscillator. So in the amplifier section you can see there is a input signal and with the help of DC power input you are going to amplify the output signal. But whereas in oscillator you don't need any input signal. So you may wonder what kind of input signal you will give to create or generate a oscillations or a sinusoidal signal. So it is called as a generator. So for a generator it delivers. So you cannot give or it does not require any kind of input signal. So the oscillator will only convert. So will amplify the signal, but the oscillator will convert DC power input into AC power, and the amplifier strengthens the AC input signal and also give output in AC, but oscillator will give or will convert DC power to the AC power. So by using regulators and rectifiers, you converted AC power into DC power. So you can consider this is a opposite of rectifier, because you are converting a DC power into AC power. So that output signal or output AC signal may be of different frequencies. You can vary this frequency, or some oscillators will give a fixed frequency signal. Here again we'll see the difference between amplifier and oscillators. So as we already seen, amplifier is an electronic circuit which gives output as amplified form of input, but whereas oscillator is an electronic circuit which gives output without application of input. So for oscillators, you don't need any kind of input signal, AC input signal. You will require a DC power supply for both of them, amplifier and oscillators, but for oscillator you don't need any input signal. Next, amplifier uses negative feedback, whereas oscillator uses positive feedback. The next comparison is amplifier operates as a multiplier. It multiplies the signal, but oscillator operates as a source, that is generator. Amplifiers do nothing till input signal is fed to the input. So as long as there is no input signal to the amplifier, you will not get any amplified output. But as here in oscillators, the moment when the oscillator is powered on, you will get a output signal. Next is condition for oscillation. So you all know the condition for oscillation. So here you can see that for a positive feedback, AVF is there. So AVF is equal to AV divided by 1 minus MV by MV into AV. So this AVF is gain with feedback, or you can say voltage gain with feedback, and this AV is voltage gain without feedback. So when you put this MV into AV quantity, when you put this MV into AV quantity to 1, then the denominator, this denominator will be 0. And when this denominator will be 0, then the overall voltage gain with feedback will be infinity, because anything divided by 0 is infinity. So this is the first condition for oscillation. So this MV into AV, so this MV into AV equal to 1 is the first condition for oscillations. So MV into AV equal to 1 is the first condition for oscillation. This quantity should be exactly equal to 1, so as to produce oscillations in circuit. Next is the net phase shift. The net phase shift around the loop equal to the 360 degrees or 0 degrees. So what is the net phase shift? So you all know in amplifier there is a phase reversal between input and output. So between input and output. The output is out of phase 180 degrees to the input. So for these oscillators, you don't want that phase reversal. So the input and output must be in the same phase, that is 0 degrees or 360 degrees. So these two conditions for positive feedback are called Bark-Hosson criteria for oscillation. So this is the Bark-Hosson criteria for criterion for oscillations. These two conditions. So now we'll move on to the classification of oscillators. So first type is sinusoidal or harmonic oscillators, that is sine wave, and the frequency range is, it is ranging from 20 Hz to 1 GHz. So as name suggests, it will produce a sinusoidal waveforms, that is sine wave, and its frequency will range from 20 Hz to 1 GHz. Then they are of different types, that is first one is tuned circuit oscillators, second one is RC oscillators, that is RC phase shift oscillators, third is crystal oscillators, and last one is negative resistance oscillators, that is tunnel diode. So from that we are only going to see two oscillators, that is RC oscillators and crystal oscillators. The second type is non-sinusoidal or relaxation oscillators. So whatever waveforms other than sine wave, sinusoidal wave, these are called non-sinusoidal oscillators. Whatever waveforms other than sine wave, that is square wave or sawtooth wave, so these oscillators are called as a non-sinusoidal or relaxation oscillators, and its frequency range is from 0 Hz to 20 MHz. From now only we are going to study only sinusoidal oscillators, that is RC oscillators and crystal oscillators. So we go to the phase shift oscillator. So this is the phase shift oscillator circuit. Now you can see there is an amplifier, a transistor, there is a single stage amplifier is there with resistors R1, RL and RE. So there is no R2 resistor. So instead of that resistor, we can see there are the three RC sections, that is resistor capacitor sections. So there are three RC sections, and you can see there is a 60 degrees, 120 degrees and 180 degrees written over there. So it is nothing but a feedback loop. You can see the output of an amplifier is fed back to the input through the RC network, that is resistor and capacitor network. You can see the output at the collector side is fed back to the input side. Here, do you see any input signal? So here don't see any input signal because it is an oscillator, it is a generator, it does not require any input signal. Here plus V is nothing but the DC power supply. You will require a DC power supply for its application. So regarding this RC phase shift network will or oscillator will operate. So here you can see each RC section will provide a 60 degrees of phase shift. Each RC section will provide 60 degrees of phase shift, and so 3 RC networks or 3 RC circuits will provide a total of 180 degrees of phase shift. 3 RC networks will provide a 180 degree of phase shift, and this single stage common emitter amplifier will also provide a additional 180 degree of phase shift, because it will convert the signal to the reversed phase. So 180 degree phase shift of RC network and 180 degree phase shift of this amplifier network. So total phase shift you will get a 360 degrees phase shift. So that your Bar-Quotient criterion will be satisfied, that the total phase shift around closed loop should be 360 degrees. So this is the phase shift oscillator diagram. So it is a RC phase shift oscillators use a combination of an amplifier and RC feedback network to produce output oscillations due to the phase shift between the stages. See, due to this phase shift of RC stages 1, 2, 3, there is a small oscillation is produced, and these small oscillations are amplified by the amplifier, and this amplified output is again fed back to the input. Then that input is again amplified, and by doing this vice versa, the output signal is amplified and you will get a desired frequency signal. So you may be wondering what exact frequency you are getting by using this oscillator. So the frequency of oscillation is determined by the selection of this R and C network. So whatever the values of resistor and capacitor you are using, you will get the frequency of oscillation, that is F equal to 1 divided by 2 pi RC into under root 6. This is the frequency of oscillations. So if you want to change the frequency of oscillations, you can change the value of R and C. It is quite as simple as that. So next part is the advantages and disadvantages of phase shift oscillator. So first advantage is it does not require any transformer or inductor. As you all know, for oscillations there is an inductor part or prime coil part is there. So for this RC phase shift oscillator, it does not require any transformer or inductors. Next advantage is it can be used to produce very low frequencies. The circuit provides good frequency stability. So frequency stability of this circuit is very good. Frequency stability means what? The variation in frequency. So frequency stability is good means what? There is not much variation in frequency. So it remains or sticks to the desired frequency. There are only two disadvantages. So for that circuit, it is very difficult to start the oscillations, because the feedback is generally very small, because you are not giving any input signal to it, and the output of this circuit is very small. So these are only two disadvantages. So to overcome these two disadvantages, what we do, we'll construct a crystal oscillator. So crystal oscillators operate on the principle of inverse piezoelectric effect, in which an alternating voltage applied across the crystal surface causes it to vibrate at its natural frequency. Means what? When you take the crystal and when you apply a alternating voltage, that is AC signal, to this crystal, it vibrates at the frequency of that AC signal. So this principle is called as a piezoelectric effect, and when you use it inversely or alternatingly, means what? When you vibrate that crystal at a specific frequency, then it will provide a signal of your desired frequency. Did you get that? When you vibrate the frequency at a specific frequency, then it will give a AC signal with that frequency of vibrations. So these vibrations, which will be eventually get converted into oscillations, and these oscillators are usually made of quartz crystal, because quartz is very inexpensive, naturally available. The quartz is abundance in our nature, availability is very much, and they are mechanically very strong when compared to other elements. So in crystal oscillators, the crystal is suitably cut and mounted between two metallic plates, and whose electrical equivalent we'll see in the next slide. In reality, the crystal behaves like a series RLC circuit formed by the components as RS, LS and CS. So this is the electrical equivalent model of the crystal. Actual crystal is there in the left hand side, and at the right hand side you can see the equivalent circuit model of that crystal. So there are resistor, inductor and capacitor in series, and again there is another capacitor which is parallel to all of them. So this is the equivalent model of the crystal. This is nothing but a series RLC circuit. So you all know, in the series RLC circuit, oscillation will take place at a certain frequencies which will occur at the resonance. So you already studied the part of resonance in the series and parallel RLC circuits. So according to them, you are going to get a frequency signal AC, that is alternating current frequency signal. So this is the general circuit diagram of a crystal oscillator, which you are going to use in series RLC platform or equivalent model. So with series RLC equivalent model, this is the crystal oscillator with the amplifier. Why this amplifier is needed? Because that oscillations, whatever crystal is giving you the oscillations, you have to increase the oscillations, and the frequency of the crystal oscillator, output frequency, will be determined by Fs equal to 1 upon 2 pi under root Ls into Cs, that is inductor and capacitance in the equivalent circuit model. So this is in general the crystal oscillator. So crystal oscillator, you can see it in your laptops or computers, even in your mobile phones. You are going to see this crystal oscillators. So these crystal oscillators have very huge role in your electronics. So next we'll see the time-based generators. So these are the time-based generator. So why these time-based generators are required? The circuits which provides a linear time scale are called as a time-based generator. Circuits provides a linear time scale are called the time-based circuits or generators. So in such circuits, either the output voltage or current, output voltage or output current is a linear function of time over a specified time interval. So meaning what? Linear function of time means what? Output voltage or current is changing, either increasing or decreasing over a linear function of time. Means what? If the voltage or current is increasing, so as the time increases, the current or voltage increases constantly, or it is whether it is decreasing, then as the time increases, the voltage or current in the will be decreasing in the proportionate manner with respect to time. So linear function means what? Current or voltage is varying with respect to the time and over a specified time interval. So this specified time interval you are going to choose. So a linear time-based voltage is required on the deflection plates of cathode ray oscilloscopes, that is CRO. So you already seen the CRO. So and you also seen the working of CRO. So inside the CRO there is a electron beam is there. So to sweep the electron beam horizontally or vertically, you will need this time-based voltage. So the electronic beam will sweep from left to right or top to bottom so instantly that you can see it is forming as a signal. So to sweep this electronic beam will require a time-based voltage, and linear time-based current waveform is required in the deflection coils of a TV receiver. So when there is a cathode ray tube, CRT TVs were there very long ago. So in that televisions, deflection coils were there, and to deflect that beam, a time-based current waveform is required in linear manner. Because of the sweep application, because it actually sweeps the electronic beam or electronic beam. So because of this sweep application, the circuits are also called as a sweep circuits or generators. So this is the applications and general description of the time-based generators. So here is the general waveform of the time-based generators. So here you can see in the first a general sweep voltage diagram, you can see there is a rising waveform and it is termed as a TS, that is sweep time. TS is nothing but a sweep time, and you can see after that the voltage or the waveform decreases gradually, instantly, not in the linear manner. So this time is a TR, that is restoration time. So that decreasing time is TR, that is restoration time, and the total time is the total cycle or total time of the cycle. So this is the general sweep voltage waveform, and below you can see a sawtooth waveform. So it is very similar to the sawtooth waveform, but it takes some time. In the sweep voltage takes very low time for the restoration time. There is a small time in restoration time in sweep voltage, but in sawtooth voltage you can see instantly it comes from maximum to 0. So this is the basic difference between a sweep voltage and sawtooth voltage waveform. So you already know output increases linearly is called as a sweep time, and the time taken for the signal to get back to its initial value is called as the restoration time or flyback time or retrace time, TR. So these time-based generators are used in CROs, televisions, radar displays, and precise time measurement system. So in the precise time measurement systems, there are these sweep generators are used, and also in time modulation. So in near future, you are going to see what time modulation is. So these are the different applications of time-based generators. So what are the different types of this time-based generators are there? So there are voltage time-based generators. So what is voltage time-based generator? That is a time-based generator that provides an output voltage waveform that varies linearly with time is called as a voltage time-based generator. Okay, as the name suggests, it is a voltage time-based generator. So whatever output voltage waveform is there, it will vary linearly with time. So these time-based generators are called as a voltage time-based generator. Whereas in current time-based generator, a time-based generator that provides an output current wave. So this output current waveform will vary linearly with time. So that is called as a current time-based generator. So whether a voltage or current is varying linearly with time, so then you are going to decide whether it is a voltage time-based generator or a current time-based generator. So these are the two basic types of the time-based generators. So from that, we'll see the voltage time-based generator. So first type is the Miller sweep generator. So this is the circuit diagram of Miller sweep generator. So this is the Miller sweep generator, that is circuit diagram, and this is the input and output relation. So in that there are two transistors. There are two transistors Q1 and Q2, and here you are going to give input signal, and here you are going to get the output signal, and the output signal is the voltage which is varying linearly with time. So a feedback capacitor is connected between the output of Q1 to the output of Q2. So this is the feedback capacitor, and these are the output waveforms for the Miller sweep generator. So here the transistor Q1 will act as a switch. So Q1 acts as a switch, and Q2 is a common emitter amplifier. Q2 is a common emitter amplifier. So now we'll go on to the processing part, that is operation. Initially, first we'll assume that transistor Q1 is on. Initially the transistor Q1 is on and Q2 is off. The output voltage, so whatever input is there, we are giving a time or a pulse signal to the input. Pulse signal to the input, negative pulse. You can see here we are going to give a negative pulse to the input signal. So when the transistor Q1 is on and Q2 is off, the output voltage is equal to the VCC. So output voltage will be maximum because Q2 is off. When pulse of negative polarity as shown in figure B is applied at the base of Q1, when the pulse of negative polarity as shown in figure B is applied at the base of Q1, the base emitter junction of Q1 gets reverse biased. The base emitter junction of the Q1 gets reverse biased. Hence, this Q1 turns off. So, when this Q1 turns off, Q2 turns on. When Q1 turns off, Q2 turns on. And as this Q2 turns on, that is Q2 conducts, the output voltage begins to decrease towards 0. So for a while, when negative pulse is applied, Q1 turns off and Q2 starts conducting, and when Q2 starts conducting, the output voltage will going to starts decreasing from VCC towards 0. Here you can see. Here. And when, because of the capacitor C1, that is capacitor C, the rate of decrease of the output voltage is controlled. So why? Because there is a capacitor between transistor input and output. So the rate of, so you know that capacitor takes a small time to discharge. So because of this capacitor, see, the rate of decrease of this output voltage is controlled by the rate of discharge of this capacitor, and the time constant is given by, here is the time constant, that is pi equal to RB into C, that is base resistor multiplied by value of capacitor. So this is the time constant. Means what? At what rate this output voltage is decreasing. Now suppose when input pulse is removed from Q1, when input pulse is removed from the input at the input of the Q1, then Q1 starts conducting, that is Q1 turns on and again Q2 turns off. Then capacitor charges quickly to VCC. Then capacitor charges quickly to VCC. So that the waveform of the generated sweep is shown in figure B. You can see here. So you can see the sweep time and fall time or restoration time in this figure B. So this is the Miller sweep circuit. Next is bootstrap time-based generator. Next is the bootstrap time-based generator. Here again you can see the two transistors. So two transistors are there. There is the input at the first transistor Q1 and output is collected across emitter of the second transistor. Output is collected across emitter of the second transistor. There are two capacitors C1 and C2. So two capacitors C1 and C2 are connected across along with the diode D. And the anode of this diode is connected to the VCC. So this is the bootstrap time based generator. Now we'll see what exactly this time based generator works. So this time based generator works exactly, or you can see similarly, to the Miller sweep generator or Miller time based generator. Only difference is there, in Miller sweep generator the output decreases linearly with time, but in this bootstrap sweep circuit the output increases with time. So in the Miller sweep generator, before the applying input signal or input pulse, the output is at VCC, but in this bootstrap time generator, before applying the input pulse, the output is at 0. So this is the basic difference. Now here you can see the output waveform. So initially we'll go to the, first we'll see how exactly this bootstrap circuit is going to work. So initially the transistor Q1 is on and Q2 is off. Therefore the capacitor C1 is charged. Therefore capacitor C2 is charged to VCC through the diode forward resistance, and output VO is 0. So Q1 acts as a switch and Q2 acts as a emitter follower. When the transistor Q1 is on and Q2 is off, the capacitor C2 will be charged to VCC through the diode and the output will be 0. Now when we apply a negative pulse as shown in figure B, we are going to see after a while, is applied to the base of transistor Q1. Q1 gets off and capacitor C2 starts charging the capacitor C1 through resistor. So when a negative pulse is applied, capacitor C2 starts charging the capacitor C1 through this resistor R. As a result, both the base voltages of Q2 and the output voltage begin to increase. Here you can see, when negative pulse is applied, voltage increases from 0 to VCC, and it is increasing in linear manner, in linearity with time. Now as output voltage increases, diode D, the diode becomes reverse biased, and this will cause the voltage across the capacitor C, hence the output voltage V0 to increase linearly with the time. So now this voltage will continue to increase linearly with time until it goes to VCC. So now when you remove the negative pulse from the base of Q1, the capacitor C1 discharges rapidly through Q2. The capacitor Q1 discharges rapidly through Q2 and the output voltage returns to 0. So in this bootstrap time based generator, the returning time is very less. So you can now RT, that is retrace time, is very low. So you will get a better sweep time. So this is the bootstrap time based generator. And next, the last one is the current time based generator. Whatever two types are we have already seen, that is Miller sweep generator and bootstrap time based generator are the voltage time based generators. Now we'll see the current time based generator. So in this current time based generator, there is a very So now we'll see the current time based generator. So in that current time based generator, you can see instead of RC, that is collector load, you're going to give a inductive load, and a diode and a resistance in series is connected across the inductor or parallel to the inductor. So this is the current time based generator. You can see the inductor is in series with a transistor and it is connected across the VCC supply. The transistor operates as a switch. So it is not amplifier. This transistor operates as a switch. So the gating waveform, that is a pulse waveform at the base, operates between two levels. That is why it is called as a gating waveform. So there are two levels. The lower level is V1 and the upper level is V2, and in between 0 is there. So this gating waveform operates in two levels, V1 and V2. The lower level V1 keeps the transistor in cutoff, while V1 keeps the transistor in cutoff, that is off, and the upper level drives the transistor into saturation. Means what? It will drive the transistor on. You know, use of transistor as a switch. So when transistor is in cutoff region, then it acts as a off switch, and when the transistor is in saturation mode, then it will act as a on switch. So V1 keeps transistor in off position and V2 will keep transistor in on position. Now we'll move on to this time based generator. When the transistor switch is turned on, the neglecting effect of the small saturation resistance RCS, so there is a very small saturation resistance is there, the current through an inductor increases linearly with time. Here the inductor is very important part of this circuit. Up till now we have seen a capacitor. Why we have replaced a inductor with a capacitor with an inductor? Because up till now we are dealing with a voltage part. Now we want a current time based generator, current waveform. So for that we are using a inductor. So when the transistor switch is turned on, the current through an inductor increases linearly with time. So during that, diode D does not conduct during the sweep because it is reverse biased. So now the growth of this current through the inductor is given by this relation, that is IL, that is low conductor current, is equal to VCC divided by RL plus RCS. RCS is nothing but small saturation resistance, RCS, minus e raised to RL plus RCS divided by L into T. So this is the relation from which you are going to get a current through inductor. where RL is the coil resistance, that is the resistance of the coil. Note that this is not a load resistance, it is a coil resistance. Thus you can see if time is very less than sweep time and this hole is very less than L by RL plus RCS, then we can write this equation as IL equal to VCC divided by L into T. So this is the equation of the current time based generator. The sweep terminates at T equal to Ts, that is sweep time. Then the gating signal drives the transistor to cutoff, that is off position. The inductor current then continues to flow through the diode D and resistor R until it reduces to 0. Now when the transistor is off, the inductor current, because why? Because inductor stores the energy, so whatever current is there from inductor, it will continue to flow through the diode and resistor until it reduces to 0. Again, when the gating waveform goes to plus V2, that is V2 level, then again the current will start increasing from 0 to maximum level. So this is the current time based generator, and I hope you all got why we are using capacitor in voltage time based generator and a inductor in current time based generator. Because in current time based generator we are actually dealing with current. We want current as a function of time, so that is why we are using a inductor. While as in voltage time based generator, that is Miller sweep and bootstrap sweep generator, we are using a capacitors. So these are the different types of time based generators and oscillators. I hope you all got the concept of oscillations and time based generators. Thank you for watching the video and thank you for joining me live. Have a good day.